Hi everyone, welcome to Art Data Science. So today we will continue from what we have seen last time, that's meta-analysis of binary outcomes. So for binary outcomes, if you remember from last videos, we have seen the meta-analysis of odds ratios, and we have also touched a little bit of meta-analysis of risk ratios. In case you haven't watched the videos, I highly recommend watching the previous videos, but if you start today, also you can stay and continue watching. Anyway, if you haven't watched, I highly recommend this part 13, meta-analysis of binary outcomes, and also this one, meta-analysis of odds ratios using meta package, and then the last one, this is part 16. I think this is supposed to be part 15, so I will leave that. That should be part 15. Part 15 is on meta-analysis of risk ratios using the meta bin package. So another one of my followers, they asked me, how do you pull odds ratios without using any package? So that means, if you remember, I think in one of the videos I was doing meta-analysis of standardized mean differences, and I was pulling them without using any package. So that means standardized mean difference, pulling standardized mean difference from scratch without using meta or any other package. So we will do the same for odds ratios, and we will use the Mantel-Hansen method. And in the next video, I will show you the Pareto method and maybe other pulling methods. Anyway, for now, just to refresh your mind about meta-analysis of binary outcomes, the association of exposure and events, exposure in case, disease, or the exposure in outcome is often measured by odds ratios, risk ratios, incidence ratios, hazard ratios, and these are mainly measures of association for binary outcomes. So that means if, for example, you take disease, so the person has a disease or not disease. Anyway, this is a traditional 2x2 table. So on this side, there is on the column side, there are the cases. On the row side here, on the left side, that means we have the exposures. So, so here, if you want to calculate the exposure, so that means the odds of a disease among the exposed. So that means A over B, or A over, that means B means NE minus A. So that will be the first part, and the second part will be the odds of a disease among non-exposed. So that means you calculate C over D, and then you get you take the reciprocal. So that means the odds ratio will be AD over PC. So that will be the odds ratio, but then the risk ratio is probability. So that means probability of disease among the exposed. So that means A over A plus B over probability of disease among the non-exposed. So that means C over C plus D. And if you take the ratio of the two probabilities, so that means you get risk ratio. That's how we calculate risk ratio. But in some cases, the risk ratio and odds ratio, they are, especially if the disease is not rare, so that means risk ratio will not be an approximate, odds ratio will not be approximate measure of odds ratio. So in that case, if the disease is rare, you can assume odds ratio and risk ratio, they are approximately equal. So that means here is a conversion formula. If the disease is not rare, then you have to convert the odds ratio to risk ratio before pulling them together. But if the disease is rare, you can pull them together. It should not be that much problem. But the disease is not rare, then you have to convert odds ratio to risk ratio. If your effect size measure, if you wish to pull all the, let's say if you have more studies reporting risk ratio and you have one study reporting odds ratio, then if you know the prevalence, you can convert that odds ratio into risk ratio using this conversion factor formula. As you can see from this formula, this is odds ratio divided by 1 minus prevalence plus prevalence times odds ratio. This is how you calculate, you convert odds ratio to risk ratio. So if the disease is rare, so that means its probability, that means proportion or the prevalence of the disease, is close to 0. So that means it's rare, maybe like 6 per 100,000 or something. So that means this number is close to 0. So if you do this calculation, this odds ratio will be divided by 1 minus 0 point something. So that means they will be approximately equal, and risk ratio will be, odds ratio will be approximate measure of odds ratio. Anyway, we have seen it already. Last time we have already said, if you want to pull odds ratio, what you need is the inverse variance method. I have already seen that. I will not go through the details. And then to pull, we take the weighted average. How do you calculate the weighted average? We take the inverse variance. So that means we take the inverse variance. So that means it will be the weight. So you calculate the variance, and you take the inverse of that variance, and that will be the weight of the studies. Once you have the weight, then you take the odds ratio, the mean odds ratio, and then you pull them by taking the pull odds ratio times the weight, then divided by the weight. So that gives you the pull odds ratio. We will do that from scratch, as I said, without using the package, and I will show you next. Limitation of inverse variance method is because if the data is sparse, or if the number of events are small and the total sample size is small, so that means you may have 0 cases, and the calculated standard error may not be estimated for the precision of the binary effect size. In that case, you have to find alternatives to inverse variance method. There are other methods. So we'll not go into the other methods. Anyway, what we want to talk today is about the Mantel-Hansen method. So the Mantel-Hansen method is a default. Actually, it's a default in MetaBin. It's a default method. But if you want to change it to a different method, then you have to specify the method. So it uses the number of events and non-events in the experimental and in the control group, or in the exposure and then the non-exposed group, to determine the study's weight. This is how we calculate the weight. But we will come back to that in the prioritization. The other one is the Pareto method. The Pareto odds ratio works only for the odds ratios. You cannot use it for risk ratios or other ratios. It only works for odds ratio. And it uses a special form of inverse variance approach. So what you do is, like here you have, as I said, kind of traditional group 2x2 table. So you have the event and then an event, and then you have the exposed and the exposed group. And this is the observed event among the exposed group. So the first thing you need to do is you have to, this is observed value, and then for this value, you have to calculate the expected value. The expected value, I think if you have the chi-square calculation, the expected value calculation is quite easy. So how you do it is like row total, that means row total, that means this NE times column total, that means AK plus EK, that means this total plus this, and this total times this, and then you get this, then you divide it by the total population, then you get the expected value. So that's how you calculate the expected and the observed, and this is how you calculate the observed, and the expected here, the observed is already here. Once you get that, you simply subtract the observed, the observed minus the expected value, and then you divide it by the variance, and you get the Pareto ratio. The variance is actually calculated this way, which means this will be that you get the row total for this. So you calculate this total times this total. That means column 1, row 1 total, column 1 total times column 2 total times so it's like you have a row 1 total here, NE, so that means AK plus BK times CK plus DK, and then you again multiply it by AK plus EK times BK plus EK. That's it. So you take this part, you multiply it with this, and then you take again AK here. So here you can see AK plus BK times CK plus DK, so that means AK plus BK times CK plus DK, that means row 1, row 1 total times row 2 total. Then you do the column totals, so that means AK plus CK plus CK times BK plus CK, that means column 1 total times column 2 total. Then the other one is like you take the sample size, this is actually square. So let's go back. So this has to be squared. This is, so that means it will be n squared times n minus 1. That will give you the denominator. That's how we calculate the Pareto odds ratio. So once you get the Pareto odds ratio, you have to take the variance, you take the inverse variance, then the weighting is quite straightforward. We will do that again, and the other one is back to generally sample size method. This one I don't even use it, but if I have time I will also show you. But that's how we calculate the weight. The weight is calculated by NTK times NCK, so that means n total in the exposure group. So that the total number of people in the control group plus total number in the experimental group, and you divide by the population. Yeah, we'll come back to that. Anyway, sometimes you may have a rare disease and you may have zero events. So in this case, if you have 0 events, the odds ratio calculation will be in trouble. So because you will have 0 in the denominator, then the odds ratio calculation will not work. In that case, you have to use continuity correction, and you add 0.5. Actually, if you simply use the semantic and the odds ratio, by default, it's simply the package adds 0.5 for you. But if you want to if you don't want to use that one, if you don't have 0 cells in your column and in your number of cases and controls, then you don't have to use that. You simply specify MH exact, so that means it will use the exact values. But I think if you don't have 0 cells, the difference will not be that much. Whether you use plus 0.5 or MH exact, the difference will be quite minimal. So you don't have to worry about that. The package will, if you use meta bin or meta package, it will do it for you. So that's how actually the last thing that I want to see is when do we use the Pareto and when do we have to use the semantic method. So the Pareto method actually works, as I said, for odds ratios only, and then if the number of observations in the treatment in the control group are balanced, if they are equal, sometimes if you do case control study, let's say, so the case and control ratio, sometimes it's people assign like 1-to-1 ratio, so that means the case and the control groups, the number of people in the case and control groups are equal. So in that case, you can use the Pareto method. Or if the event is rare, let's say if the prevalence of the disease is rare, so that means only 1%, or let's say 2-5 cases per 100,000 population, then you can use the Pareto method. And when the treatment effect is not overly large, if you have overly large treatment effect, then the Pareto method will not be a good choice. But if that treatment effect is not overly large, then the Pareto method is actually kind of jointly a good choice. And if the event is rare, as I said, you can use. But the Pareto method it has been criticized in many papers. You can look at the literature. Some have written that it's not. It's causing. It's not producing a reliable kind of disease. So it has been criticized already, and you can take a look at the literature. I think for today, what I want to do is I can simply jump into the section. It's a hands-on tutorial, so let's use the most primary outcomes. That's what we want to do. And here are the packages we need. We need data for some data manipulation. And then, as I said, this is how we calculate the odds ratio. We have already seen that. I will simply rerun some of the things that we have seen in the previous video. And then for today, I will simply go into the section that we want to see. So that means pulling odds ratios from scratch without looking at any package. Here we are doing them using our package data. But I will show you without using any. So here is the data, how the data looks like. So we load the data. So here we have the studies, and here we have the number of events and in the exposure group, and the total number of people in the exposure group, and here we have the number of events in the control group, and here we have the number of events in the total number of people in the control group. So that means if we change that into this kind of format, so this is the value we have, the total for NE. So that means this one is here, NE, and then EC, is here. So you can have if the disease, let's say, present, absent, and you have the exposed and unexposed group, and this is how you calculate the total in the disease side, and then in the exposed side, this is how you calculate EE. This is the total population. So to get, because we have the total here, but we want this one, so that means A, B, C, D. You know, if you know the odds ratio table, I mean the contingency, this 2 by 2 table. So to get the odds ratio, the simple calculation is like A, B, B, C. So that means this times this divided by, and this one times the other one. Bring it back. Yeah, so this is how we calculate the odds ratio. The next thing is we calculate the standard error. The standard error calculation is very simple. The standard error for log odds ratio, you take the reciprocal and you sum the reciprocal of each one here on each of these events, and then you take the square root, so you get the standard error. But if you take the square, well, that means without the square root, then that one is the variance. And the other one is the next thing that we need is we need the weight. The weight as we have seen before, so we take the inverse variance, so that means we simply take the inverse of this value. So that means if you calculate this and you get the inverse, so you get the weight of the studies. Once you get that, the log odds ratio, the pooled odds ratio will be simple. So that means you multiply this value with this for each study, and then you sum them. You take the summation and you divide by the summation of the weight. So you take the summation of the weights, and here you take the weight for each study. You calculate the weight times the log odds ratio, and then you take the sum of all of them. Then once you have that, you simply divide that value with the total weight, and then you get the pooled odds ratio. So this is how you pool odds ratio. Once you have that, calculating confidence interval is again, I mean, you take the exponent, of course. You have to exponentiate it back, because this is you take the odds ratio, you take the log odds, and then the log odds times, because here you see there is log, then you exponentiate, and then you get the odds ratio. But to calculate the confidence interval, confidence interval is calculated by effect size plus or minus 1.96, because we have 95% confidence interval z value, z alpha over 2 is 1.96. So effect size plus or minus 1.96 times the standard error. The traditional confidence interval calculation. So once you calculate this, then confidence interval calculation will be quite easy. Or you get the weight, so that means you get the variance, and if you take the square root, and then if you take the sum, then you get the standard error. Or you simply take this weight and you simply sum it. You take the summation of the weight and you take the square root, you get the standard error. That's how you do it. You have to reciprocal, of course, you have to inverse it. If you inverse it, you get that one. So I already created a function for all of these formulas. Here we have the function, so we need the values we need are these ones, of course, as reported. These are the values that we need. Then once we have that, we calculate the log odds ratio. So the log odds is calculated simply by 80 times BC, 80 over BC. Then once you have the odds ratio, then we return the log odds ratio. Similarly, I also created a function for standard error of log odds ratio, and to get that, we simply need all these values again. We need all of them, and then the formula is this. So we take the square root of the inverse of each value. And then we take, that means that will return the standard error of the log odds ratio. That's how we calculate the standard error. And then finally, what we need is the weight calculator. So this is the weight. I mean, here we have the weight, so that means 1 over variance. 1 over variance of the log odds ratio. That's how I calculate the weight. So you have, so the variance is calculated this way, as explained here. Variance 1 over A, 1 over B, plus 1 over C, plus 1 over C, 1 over T. So get that value. Once you get that value, then it's simple. 1 over EE, as it is here, 1 over EE times 1 over NE minus EE plus 1 over EC plus 1 over NC minus EC, because we want the other value, because this is not risk ratio. I mean, this is actually designed for risk ratio, not risk ratio. That's why we have to calculate the other values instead of the total. So once you get that, then we take the inverse, because this is variance. If we want to calculate the weight, we have to take the inverse variance. Then you get the weight. So what I want to do is, let me just create a few cells here. So we have 0 for the TF. Let me call my TF. Let me call it log odds ratio. The log odds ratio would be calculated by log odds calc or rcalc, and then let me call this. Actually, I want to take some value here, because my data frame is called DF. My data frame is called DF. So I take all these values, then I get the log odds ratio. So I get the log odds ratio. The next thing that I want to calculate is the weight. For the weight, I have the weight calculator that I have here. The weight. So what I need is the weight calc times, of course, the complete. Actually, I simply take this and then place that one here. So I take this here, and then the weight calc. I call my function the one I just wrote. The weight. Where do I have it? Yeah, it's called with weight calc. So that's my equation. My function, I call that one. No, that's not what I want. I simply want this function here, the weight, my weight calc. So like this. So if I run them, I get the weight. The next thing is, maybe I can also take the standard error calculator, and maybe I can simply write something like this: standard error. Let me call it this way. Or I can simply standard error. Standard error. Then I get all these values. Once I have that, I simply run. So now there's something wrong here. Maybe I didn't run it yet. So let me run this. And now if I run this, I will get my values. So that means if I get this, for example here, df log odds ratio, So I should be able to, here are my, actually if I get count maybe or select, I can simply select, should multiplier select, I take my study, I think that's the first variable, study, and then low voltage ratio. Low voltage ratio, then what I have is weight, and then I have the standard error, is E. Yeah, so here I already have the low voltage ratio, the weight, standard error, and the study. So that's all I need for calculating the pooled voltage ratio. So for the pooled voltage ratio, the formula is here. You know, this we take the sum of the weight times the log voltage ratio, and then we divide it by the summation of weight. Maybe let me calculate first sum of weight. Yeah, sum weight is like total weight. Total weight I calculated this way. Sum df I already have weight. What did I call it? Actually I call it weight. So obviously this Jupyter notebook is not detecting it anyway. This is how I should calculate the weight. If I run this, and simply if I print this one, actually I will get the total weight. So here I have the total weight here now, and then the next thing I want to do is pooled log OR, log voltage ratio. The pooled log voltage ratio is actually calculated by this formula. So you take this, you sum the weight, each individual weight, by each individual log voltage ratio, then you take the summation, then you take the weight, you divide it by the weight. So the pooled voltage ratio is calculated by sum, you take the sum of what? df weight, should have weight, times df log voltage ratio. So you have log voltage ratio. Then we divide that one by what? By this total weight. We already have total weight, or we just simply take this one here. Log voltage ratio, df weight times log voltage ratio. Then we take sum is not right. Now we take pooled voltage ratio, we simply print that value, and we have to see, we have to get the pooled or log voltage ratio. But we have to exponentiate it. So we have to take the exponent. Then maybe let me exponentiate it. Then once we have exponentiated, I can simply also round it maybe 2 significant digits, otherwise it will be really long. And then we see how much the value is. So that's not right. Round. Yeah, so we have voltage ratio of 1.32, and then for the confidence interval, what we need is the standard error. For the standard error, the formula is here. So standard error log voltage ratio equals this, but we have the variance, we get the weight, we can get it from the weight. So that means we take 1 over variance log voltage ratio, we take the reciprocal of this, and then we put it in the square root. So that means we get the standard error. So to get that, let me calculate standard error. Actually, let me simply assign to standard error. Actually, I don't have to assign it to the value like this. Then for standard error, how I calculate it is I simply take the total weight, I put it in the square root, and then I take the inverse, then I get the standard error. That's how I calculate the standard error. Once I have the standard error, let me print it. Then maybe I can also round it to 2 significant digits if you want. So here, maybe I'll take this, simply print it. So here I have the standard error. That's my standard error. The next thing is I want to calculate the confidence interval. So we have the expected, the voltage ratio. That's here is our voltage ratio. But now I want to calculate 95% confidence interval. 95% confidence interval is calculated by this formula: effect size plus or minus this z alpha over 2 at 1.96 times standard error. So this is the formula for 95% confidence interval. So what we do is we take this value, the pooled log voltage ratio, and then we take this pooled like a total standard error. So to do that, let me call this paste function. And then paste. Then what should I do? First thing I want to paste, I want to include in my is 90, this one, log voltage ratio. Then I call 95. What is that called? Maybe I add comma. Then the next one is I simply call 95% confidence interval. And then the next one I will calculate the lower bound. Maybe I do it here. The lower bound would be the lower side of the confidence interval would be this plus 1.96. This minus 1.96 times the standard error. That's my lower bound. And maybe I put this one in brackets so it doesn't get confusing. Then the next one is upper. Lower, let me call this lower. And the other one upper. I will simply take this and change a few things. Upper, then I call this plus. Now, if I simply put this, if I get the lower, print the lower, then the upper, for upper. Maybe I can also print that effect size. No, that was not effect size. What did I call it? I didn't assign it to a value. I can simply call it this one, this 1.32, which I will get in the end. Let me print it here, and I should remove this bracket here. Now, if I get this value would be the full voltage ratio, and this one would be the lower, and the other one will be the upper. So let me run them. So I get voltage ratio of 1.32, and the lower bound is 1.138, the upper is 1.196, doesn't look right. Maybe I have some errors here. Okay, here standard error square root of 1 over total weight. So it's 1 over variance. Look, that's my weight, and to get it into standard error, I will simply okay, I forgot to take the square root. So here I already did, didn't I? Yeah, okay, 1 over total weight. Actually, this value should be square root. So, or we can also calculate it actually with our function here, standard error calculator, and then we simply take the sum. Or another way around, what we can do is we simply take the square root of, we take the sum, and then we take the inverse of the weights. What is that? The weights. That should be, yeah. So we take the summation, and then we take the sum of the weight, and then we take the square root, so then we get the standard error. Another way around, you can also get it with the function that I supply here, with this one, like this here, standard error, then we use that value for calculating the confidence interval. So now we have standard error. Now we should be able to get the values somehow. Yeah, this is exponentiate, and then no, we have to actually the pooled log odds ratio minus 1.96. Now I take the exponent. Then I also do the same here, because the log odds ratio, here we have the log odds ratio plus or minus 1.96 times standard error, and then we exponentiate that. Once we have that, then we have the upper and the lower confidence intervals. So here we have exponent, standard error, square root sum over 1 over d of weights, pooled log odds ratio. So we have exponent pooled log odds ratio minus 1.96 times standard error. Then again we also have it here. Now I should get that values correct. Yeah, actually we made a small error here. So we take the square root, and then we take the 1 over the sum of df weights here. Then you get the standard error. So now we should be able to have everything. Maybe we can also round it. This one, then we really have this long digit. Round to two significant digits. Usually it's recommended to report odds ratios in two significant digits. Now we should have everything in. What did I do? What did I make an error here? Round. I'm not Jupyter notebook is adding a few additional things. Yeah, so here we have the full effect size 1.32, and the lower bound is 1.1, the upper is 1.59. So the other thing I want to do is let me put everything in here. So first thing we take the pooled log odds ratio, and then we exponentiate it, and then the next one is I want to get the lower, then the upper. Probably I would put it in a square bracket, upper actually. So I already have. So let me create a square bracket, this kind of square bracket, comma, and then maybe in between I need a bracket, I need a comma, like this. Then at the end I close the square bracket. So that would be the square bracket. Now if I run that, I get the pooled odds ratio 95% confidence interval. Maybe I add a separator. Let me add just space. Now I have everything. Okay, I should also round this. Maybe I can round it here. I don't want to have that long number. Round to. Now if I run that, I should be able to get my confidence, the effect size, 95% confidence. So that means 1.32, 95% confidence interval is between 1.11 and 1.59. We have already calculated, we have already seen the pooled meta-analysis in the previous video. So here, if we use a meta package, so here this is what you get, 1.33. That means a fixed effect model. I think what we did now is a fixed effect model. Then so you get the 1.33, and then you get the lower bound is 1.11, 1.58, almost the same as what we just calculated here, without using any package. So here we get everything. Yeah. Also the weight, so you can also get this. Actually, you don't even have to use forest plot to display this. You can also use using the values we have. So if I show and select, if you get the variables and display study, the other one is like whatever, log odds ratio, log OR, log OR, and then what we have is a weights, I think. So weights. So this is it's taking a little bit of time. What did I do? Calculating that the log odds ratio doesn't exist. Okay. Log OR. Okay. Log OR. I have log OR. That's log OR. Okay. So that's how I calculated that one. Now again, weights doesn't exist. Okay. What do I have then? Okay, that's weight value is here. So if I print them, then I get my tables. So here I have the study, here I have the weight, log odds ratio. So once you have that, I think that you have everything. You can also calculate, of course, you can also calculate confidence interval for each. Similarly, you simply take the reciprocal of this, you get the standard error. I mean, you take the reciprocal of this value and you put it in the square root, and then you get the standard error. Once you get the standard error, that means you, yeah, maybe we can also do that actually. if you want, what we can do is we can df lower equals, that means we take the weight, that we take the square root of that weight, so that means the square root of 1 over df, that's a weight, because we want to get the standard error. The standard error is calculated this way. So now we have the standard error. The next thing is we need the log odds ratio, minus, because we are in the lower side, and the upper would be plus. No, but not like this. We also need another value. That means that's 1.96 times. So we take again, we put this in bracket to avoid some confusion. Then I can simply take this and replace the other one actually. So here, then because it's upper confidence interval, I have to change this to plus. So now we have the lower. Probably it's a good idea. We can also round it by 2 significant digits, and then again just one by round 2 significant digits. And again we can also exponentiate it, because we want to see the confidence intervals that's in the odds ratio scale, not in the exponential scale. So now the other thing we need is, now we need to calculate the odds ratio, EF odds ratio. To get the odds ratio is we take the exponentiated form of the log odds ratio. So df log OR. Yeah. Now we have everything. So I simply turn this off, and then study odds ratio, lower and upper, weight. So now we have everything. Log odds ratio doesn't exist. Of course it exists. What is it thinking? This is what we have, yeah? Yeah, so log odds ratio. We should have that value, don't we? Yeah, so we have this value, log. Not log OR. Yeah, we have log odds ratio. Okay, so here df OR equals exponentiated form of df log OR. Was it not working? Object log OR doesn't exist. Yeah, okay. Now I realize that's because we didn't call this dollar sign. It's beta thing. Okay, you can also use this mutate, but I'm using this beta. So now we should have everything, but not yet. Okay, 1.96 for round. That's not correct here. Now if I run that, I should get my everything here. Maybe it's also a good idea to approximately get the weight. I can get that one, the lower and the upper confidence interval. df log OR plus. Okay, I made some error here. Okay, log odds ratio, round 2, and then let me see. Okay, now I get the upper. Okay, so I should again put this in bracket, then round. Okay, maybe I put that round at the end, because otherwise I have to call another round. Okay, that's the problem. Yeah, maybe I don't need that bracket actually. Same here, round 2. So instead I put this one at the end after the exponentiation. Then I have only everything in 2 significant digits. Yep. Now if I run that, then I should be able to get. But there's obviously some error here. df. Okay, I don't need this bracket. Now it should be, yeah. But still the upper, the lower, and the lower is not right. The lower has to be exponentiated here. Well, okay, with the pipe, maybe the reason, that's the reason. So I simply take the exponential here at the beginning, and at the end I will simply exponent. Again here, exponent. Then let me close this bracket. Now I should get the confidence interval values. Okay, let's take some error. Yeah, because I'm calling another exponent here. So now I should get everything. Yeah, now I have the odds ratio. I can also round that one in 2 significant digits. Yeah, here, let me round it here. And then maybe the weight also, we can round it. And then maybe we can multiply it by 100. So to get it in percent, so to say. Yeah, there must be some error here. Round, weight, somewhere OR not found. Yeah, okay, let me leave this rounding because I'm putting it inside the select function. Maybe that's the reason it's not working. Yeah, let me close this again. Or maybe I can actually multiply it. Yeah, no need to do that. Yeah, anyway, so we have the weight, the odds ratio. Maybe let me do this, df odds ratio, round df odds ratio into, and then then the weight, df weight, actually, round df weight in what? In 2 significant digits, but I have some errors here. Jupyter Notebook is writing faster than I do. Now I should get all the values in 2 significant digits. So here we have the estimates, then we have the confidence interval, lower and upper, and then at the end we have the weight. So we have all the weights. So we have all the weights. I mean, if you add all of this, it should come to 100% actually, to 100. Yeah, and then we have the pool to odds ratio. If you are good in ggplot2, you don't have to use a forest function. Then you can plot this in yeah, you can plot it in a forest in a ggplot2, like error bar, Joule error bar or something with long point and error bar. You can be able to do the plotting even without using any package. But that's how you calculate the risk ratio, odds ratio, without using any package. The Mandel-Haenszel method, that what I show you is just a Mandel-Haenszel method, but the Pareto method we'll do it in the next session. But that's really to the basic of pooling, and without using a package, you may not practice this in your day-to-day meta-analysis. You may just use the package, and the package is doing it for you. But it's a good idea to know it also how you do it without using the package. Yeah, that's all for today. It's a little bit longer session. Maybe for the next one it will be shorter, and maybe in shorter videos to make it more interesting actually. So thank you very much. Keep supporting the channel and keep spreading nice words. Thanks, and I really appreciate your feedback.